Manuel Blum is the Bruce Nelson Professor of Computer Science at Carnegie Mellon University. He received his bachelor's and master's degree in ECS in 1959 and 1961 at MIT. Later, in 1964, he got his PhD in mathematics under the guidance of Professor Marvin Minsky, who won the Turing Award in 1969. Professor Blum won the Turing Award in 1995 in recognition of his contributions to the foundations of computational complexity theory and its application to cryptography and program checking. Among his prominent results are the compression theorem and the Blum speedup theorem, a protocol for flipping a coin over a telephone, the Blum-Blum-Shab pseudo-random number generator, the Blum-Goldwasser crypto system, and CAPTCHAs. Professor Blum had over the years many PhD advisees, most of whom became prominent computer scientists. 4 of them were invited speakers in the Israel CS Theory Days: Shafi Goldwasser, Ronit Rubinfeld, Ryan Williams last year, and Moni Noor this year. So I would like to welcome Professor Manuel Blum. I do not reveal the title of his talk because he wants us first to see other things.
You said coin flipping over the telephone, but we have Adi Shamir over here who did poker over the telephone even before I did coin flipping over the telephone. So anyway, thank you. Let's see. Good. Let's see. So you've seen things like this: 1, 4, 9, 16, 25, 36, 49. What comes next? 64. After 49, what comes next? 64. Okay, 2, 3, 5, 7, 11. What comes next? So you got the primes there, so you got the squares, the primes. 3, 1, 4, 1, 5. Pi. So it's good. 1, 2, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5. Yes. How about this one over here? One. It would help if I drew it as a triangle. 1, 2, 1, 1, 3, 3, 1. 1, 4, 6, 4, 1 is Pascal's triangle. You get, you'll be seeing demons later on, which infer these things. And what the demon would notice is that the low numbers are important. The ones occurring there, it would split this up into 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and it knows enough to then put it in a triangle and then to figure out what's going on. How about 3, 2, 7? 24, 59, 118. You want. Can
I see if it works? This one. Can I see?
Well, do you mind if I point the? Okay, good. So you've seen things like this. When I remember when I was in high school taking one of these IQ tests. And getting something like that, not knowing what to do, and it really bothered me that I didn't know what to do. So I went on, and I must have learned something in the process, because when I came back, I realized, oh, taking differences might help. And I have no idea. Oh, point. Taking differences might help, and so you all know that if you take differences and get down to a constant, then you can work your way back up and keep on going. How about this one? This is a rather interesting sequence. It's one that's used to prove that was used at one time. It was part of. There was a rule in chess at one time that if the same sequence of moves occurs 3 times in a row, it's a draw. And this sequence was used to prove that that does not cause, that does not make chess end, because here's a sequence in which no string occurs 3 times in a row. You have 0, 0, 1, 0, 0, 1, but then it's 1, 0, 1. Anyway, how do you generate this thing? The way the machine works is that you first notice something about this. There will be, as you will see, a daemon that is looking for periodicities. And in this case, it will notice so there's a period 3 daemon. And what this period 3 daemon does is to break this sequence up into 3 sequences. The first sequence being the first, the fourth, etc. element, then the second and the third, and here it's it's noticed, this is supposed to be red, that a 1 is occurring every third element is also 0. Pseudo period, you know what it means for sequence to be periodic. What is pseudo period? I won't define it, but a sequence like 1, 2, 1, 3, 1, 4, 1, 5 is pseudo period 2 because you can split it up into 2 sequences. One of them is all 1s, and the other is 1, 2, 3, 4, 2 simpler sequences, and that can be turned into a definition. So here, the 0, 0, 1 is, oops, I don't know what I'm doing here. Okay, so the 0, 0, 1 appears in the beginning, the 0, 0, 1 occurs again. The daemon, one daemon will see that this is the constant sequence, another one sees that this is the constant sequence, and there will be another daemon looking at this and looking back to see if it ever appeared before, and sure enough it appeared up here, and that enables you to generate the rest. Okay, so how about this one? What?
It's a counter.
Counter.
Binary counter.
The binary counter. Oh, that's good. That's good. Yeah, it's a binary counter. So, yeah, it's the binary number 0, 1, 2, 3, broken up into individual digits, and nobody ever gets that. So that's very good. In fact, one of the demons. So there are many ways to try to infer something like that. One of the demons, which generally works very well, and I'm giving this as an example, something that does not work. One of the demons it says, when you have a sequence in which some symbol occurs several times, count the number of times it appears. So there's 1, 0, and then there are 2 1s, and 1, 0, and then there are 3 1s. And this thing would write this down as 1, there is 1, 0, and then there are 2 1s, and then there's 1, 0, and then there are 3 1s. And well, at least the second sequence you recognize, that's very easy, 0, 1, 0, 1. And well, what about the top one? Again, you can do stuff. There are demons that will notice, in this case, that, for example, this 2, 1, there's a demon, as I mentioned, for the low numbers, and there's a demon for the high numbers, and it notices that the 2, then the 3, then 4 are the high numbers here, and the 2 is followed by a 1, and the 3 is followed by a 2, and the 3, and the 4 is followed by a 3, and that can eventually lead to a solution, but another demon notices what's going on well before that one gets done. Okay, so title of talk. So here's what I, by the way, thank you, Tamir, for inviting me. This is the first time that I've actually been at a conference giving a talk at the same time as my son, Avram, and I really appreciate that. That's great. Avram and I were talking this morning, or a few days, and it was clear that we should talk to each other more because so most of so I'm going to talk about deductive versus inductive inference. Most of what mathematicians do is called deduction. You know, you prove theorems. It's great. It's wonderful. The proofs are lovely, and I love them. But of course, it's not the only thing that mathematicians do, but it's mainly what they're thought to do. And inductive inference is what physicists are said to do. It's not the only thing. They do a lot of deductive inference too, but inductive inference is from experiment and observation, inferring the laws of nature. And so this is Galileo swinging on his chandelier, And this is a typical sort of thing that that comes up in physics. You have a pendulum here, and you might want to find out how the period of the pendulum depends on the length of the rod and on the mass of the bob. And I actually did this experiment myself just a couple of days ago, just to see. Did you know you take a 1 meter long string and you let the thing go? It takes about 1 second period. So it was very rough, but wow, I thought maybe the 1 second and the 1 meter are related because of the pendulum. I don't know. Anyway, these are the sort of numbers you get. And the point is, if you don't know and you don't have Newton to tell you what to do, you might want to be able to figure out what's going on here and infer. You know, you try in essence guess what it is that's going on here. Okay, so clear what I mean by inductive inference? So I'd like to model, so this talk is going to be about inductive inference. Most talks, most computer science, all computer science is about deductive inference. I'd like to get into this inductive inference. And in fact, not only am I going to get into inductive inference, no theorems or proofs in this talk. All I'm going to do is induction. So this is a very weak computer science talk, but anyway, here's my model of inductive inference. So I view the physicist and the world as Turing machines. The physicist is a Turing machine. The world is a Turing machine, and the physicist wants to understand the world. See, physicist. That's for me the physicist, and there's the world, and he wants to understand it. The way the physicist does it is he computes somehow, gets an input X, feeds it to the world, or whatever part of the world wants to understand, and the world sends back a Y. And it's the job of the physicist to try to figure out how that Turing machine works. So feeds the world x1, gets back y1, feeds x2, gets back y2, and basically that physicist wants to be able to determine the rule for generating this. And we say that the physicist wins if it indeed converges on an algorithm that's correct, right? Converge on an algorithm that's correct. Of course, it's a funny thing, this induction. You never know, of course, that you're right. There's no way that you can't prove that F equals ma. You can disprove it if it's wrong, but you certainly can't prove it. You can just give evidence for it, and the same thing will be true here. So the physicist himself doesn't know if he's converged on the correct answer, but if he has converged, if God looking down sees that he has converged, then we say that that physicist wins. So that's the model of inductive inference. It's somewhat like machine learning. Yes?
How do you interpret not halting in this context?
That's
Respect to physical reality.
it's very interesting. So I mean, that can obviously happen, but generally when physicists are doing experiments, they are getting back something, and I won't go into it now. It actually does come up, maybe even in the next slide. When we're talking about efficiency, okay? So this is the model. What does it mean to say that the physicist is efficient? Well, it's efficient if there exists a polynomial such that the physicist converges to a correct algorithm after making at most polynomial number of mistakes. So I want the convergence, the number of mistakes to be polynomial in n, where n is the size of the algorithm that actually is the world's algorithm, right? The physicist has the world there. The world has certain size, certain number of states, and the physicist is allowed to make at most polynomial of n mistakes. And that's important for this. And the physicist has to also run in time that's polynomial of the time that that the world is taking on the input. And there's a point that I had already made. The physicist does not know, cannot know when it has converged. I don't know. Is that okay? Not clear. Go ahead.
Actually, I was wondering about the issue of size. What about randomness or noise in the physical world?
Yeah. Good. So I'm taking the easy way out. Like those sequences that you saw before, no noise. I simply am not having any noise, and I'm assuming that the world is completely deterministic, Newtonian kind of world. So obviously, that's because I don't even know how to deal with that. So the learning people, machine learning people, do deal with questions of noise, and they deal with much harder sequences. I'm dealing with a much easier class of sequences that are wholly deterministic. But I do want to get exactly the right answer. I don't want to get probably approximately correct. I want the correct answer, which would, in order to do this. This is not quite right, by the way. So but it's, oops. Oh yeah. Does this look red to you? No. Fortunately, it's dark. Anyway, this is a slight modification because I don't know how to get a physicist. I don't know how to construct a physicist that can infer all sequences, but I can at least construct a physicist that's efficient on a subclass of sequences. That on a certain class of sequences will have this property that if you have a sequence from the class, on sequences in the class, the physicist will converge on a correct algorithm after making at most a polynomial number of mistakes, and that physicist will converge in the right amount of time. Okay, so, all right, let's go on. Getting the model clear. See, all Turing machines, including the world and the physicist, are deterministic. It's going to be even easier. I don't want to get into the business of how the physicist decides what experiment to do. Okay, I'm going to be sort of, when Kepler was trying to figure out the orbits of Mars, he already had the data. He was not doing the experiment himself. Tycho Brahe had done that. He had the data, and I'm trying to do something like that. How did Kepler manage to come up with laws from this data? So I'm going to assume here that the inputs are 1, 2, 3, 4, 5, 6, which is very nice, and in this order, so we're not allowing the physicist any flexibility in this talk, at least not today. Not tomorrow either, because I really don't know how to deal with this in general, but it's another matter. In this talk, the physicist seeks to hypothesize correct algorithm for the sequence y1, y2 that the world outputs on inputs 1, 2, 3, 4. Tamir, is that okay? No, alone. I'm going to be asking you questions. I'm going to be pointing to you again, young man. You're going. Okay.
Excuse me. At what point do you expect the physicist to come up with an algorithm after how many experiments?
He keeps on going forever.
Forever.
He keeps on going forever. It's like those sequences you saw at the beginning. Yeah. Like it just keeps on seeing, and at some point it is guessing in advance the correct answer, and he doesn't know that he's actually figured it out, but God, looking down, sees that yes, he has figured it out. It has figured it out. This keeps on going forever. You don't like that, huh? Forever. It's just like physicists even today. Did you know they're still trying to see if F equals ma in tiny small?
Yeah, Yeah, but physicists live for a constant number of years. So the question is, do you have any restriction here on at what stage you expect the physicists to come up with?
All I want is that in the process of doing the experiment, it makes it most polynomial of n mistakes, and it runs in a reasonable amount of time, not much longer than the world does. You know, it should run. I don't care if it's what time it is, but not much more than the world takes. So that's an important part of physics. A polynomial number of mistakes is important because it's relatively easy to do this with. If you allow exponentially many mistakes, don't want to do that. Where am I here? Oh yeah. This is so. About 30 years ago, I had a graduate student, Dana Anglin, and she and I would go around. We were trying to figure out what sequences graduate students in computer science can infer in 10 seconds. I called them 10-second sequences. You see, so like 1, 2, 1, 3, 2, 1, 4, 3, 2, 1. That's easy, right? You can tell me what comes next. How about this one? 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Okay, and the next one, 1, 2, 2, 3, 3, 4, 4, 4. See, 10-second sequences, and basically those were good. This next one was not a 10-second sequence, so we already saw that. That's the Pascal triangle. That's an example, not a 10-second sequence. We wanted to see what it is, it's sort of a psychological thing. What is it that computer science graduate students can see right away? There's another source for my sequences. Sloane. Have you ever used Sloane? Sloane is fantastic. It's OEIS, Online Encyclopedia of Integer Sequences. Oh, I love it. When Sloane's about my age, a year younger, he's got this wonderful stuff. When he was a graduate student, he started keeping sequences that came up, and he actually published a book, 2,500 sequences that had come up. He was very careful. He only allowed himself 3 to 4 lines per sequence, because if you allow another, I think it was 3 lines. If you allowed yourself another line, it makes that book a lot thicker. So he had to be very careful. He would take a sequence. He'd give you the first however many numbers. He would give you a very nice description, of what it is. And he published this book. And then about 10 years after that, he published another book because he had come up with a lot more sequences. People had suggested things to him. And at that point, he had 5,500 sequences. He's up to 200,000 now. He's had some help. Just imagine, 200,000 sequences hand-labeled with a short description and a reference and a formula if he can get it. And it's a wonderful compendium. It has any sequence, any integer, algorithmically generated infinite integer sequence that has ever been published. It doesn't have all the 10-second sequences because they haven't been published. But every time I mention a 10-second sequence to him, he puts it in the book, in the encyclopedia. So here are examples, 1, 2, 3. Oh, by the way, here's how I like to use this online encyclopedia. If you've not used it, you've got to try it. It's just wonderful. You put in 1, 2, 3, and I take its top hit to be its guess as to what comes next, which is what alone? 4, right. So any reasonable human being says 4. Oh, the Sloane Encyclopedia says 5. And why? I presume it's because there's more literature on the Fibonacci numbers than there is on the natural numbers. And it seems to be based, from what I can tell, on the amount of literature there is. So OEIS thinks that 5 is next. You put in 1, 2, 3, 4, and then it says natural numbers. It's really, it's like an automated physicist. You can put in 1, 1, 2, 2, 2. What is this thing? 1, 1, then 3 2s, so 2 1s, 3 2s, 1 2 3 4 5 3s, 1 2 3 4 5 6 7 4. You know what it is. What? 9. After 1 2 3 4 5. You don't recognize the primes? What? There happen to be, there are 2 1s, 3 2s, 5 3s, 7 4s. The next, sorry, I thought you were still back here and you were there. You're ahead of me. Okay, good. So that's, so you look it up. It's amazing. I mean, you look it up, there it is, 83,375. It was put in after the second book, but long before it came to 1 2 3 2 1 2 3 4 3 2 1 2 3 4 5 4 3 2 1 2 3 4 5 6 5. There it is. Here, so I had to work for a while to be able to come up with an example for you that it's not there. Here's an example that's not in Sloane. Please do not tell Sloane this, because if you tell him, he will put it in his book and then have to look for another example. This is 1 followed by, you see, this is the sort of sequence that this daemon that does counting. It sees a bunch of zeros that counts how many. So it sees that there's a 1 0, then there are 2 zeros, and there's 4 zeros, and there's 1 2 3 4 5 6 7 8 zeros. What's going to come next? 16 zeros. Not in Sloane, though. Sloane has just 200,000 sequences. It's got polynomials, like the squares, 1, 4, 9, 16. It's got lots of polynomials. You put in x cubed minus 3x plus 1, it's there. And you have to look a bit to find, but you will find polynomials that are not in Sloane, because it's finite. There are infinitely many polynomials. So that's the problem. It's finite. And so here's what I want. I would like to replace the daemons. I view every sequence in Sloane as a kind of a daemon. This daemon is on the lookout for that sequence. And if you put in that sequence, boom, it latches onto it, okay? And what I would like to do is replace each of those by a slightly more powerful daemon. I'd like to understand the class of sequences, like the polynomials, and have a single daemon that will recognize any polynomial. And I need this for my automated physicist. Okay. So here's decimal expansion of pi. By the way, this one can be decimal expansion of pi. That comes up before this next one, which he put in after I told him, well, 3 1 4 1 5 1 6 1 7 1. That's a 10-second sequence. Stuck it in 57,979. Okay, so what is this about? Oh yeah, that I'm viewing. How much time do I have?
16 minutes.
16. Okay, so this is Sloane's online encyclopedia. It's a kind of automated physicist, and I just want to make it a more powerful kind of thing. One which knows about stuff like polynomials and differencing. My goal is to replace, it may be viewed as a program in which each sequence is a daemon. Yeah, I said that. My goal is to replace each such daemon by a more powerful daemon capable of inferring a whole collection of sequences. And then I want these daemons to work together. So basically, what I'm having what these daemons do is they see a sequence, like like remember the 001, 001, 101. There's a daemon that splits it up into 3 sequences, and then the other daemons look at, some daemon says, oh, this is all zeros, another one says this is all ones, another one says, oh, this is the sequence we had at the start. The daemons work together to be able to infer sequences.
What does it mean working together? Because they are competing against each other.
They're competing.
There's a polynomial demon, and any sequence will suggest some continuation.
Yeah, yeah. So this is a very important part of this thing, Adi, that for which I don't have a good answer. I would like to be able to say how high the demon should raise its hand. Like if you see there's a demon that thinks a sequence of polynomial degree d, and it tries polynomial degree 0. All constants, fine, but if it's not, tries polynomial degree 1, it always has an answer. But really, it shouldn't raise its hand until there's some evidence that the sequence is correct. And I don't know how to determine how strong that evidence is yet. That has yet to come. It doesn't stop my students from programming these things. I will. Okay. Oh, applications. So a bunch of applications. You know, I mean, why am I interested in this? You know, God knows. But have you ever heard of LINCOS, Language for Interstellar Communication? This guy, Hans Freudenthal, was a logician, a pretty good logician, and he wrote this book, LINCOS, which is a string of bits, one string of bits, and he said, if you want to speak to an alien in some other galaxy, well, some other planet, that would be far difficult enough. It's very hard to communicate. You basically send one sequence, and you've got to understand from that. And if you look at that LINCOS, you see how it starts gradually developing some information, and along the way, it produces these sequences. Each sequence, the first one is 1, 2, 3, the unary numbers up to 16. And the second one is 1, 4, 9, 16, stops there. It gives it a name. Of course, we would call it the squares. He gives it a name. So this name can then be used later on. And then he gives it this sequence, which happens to be the primes up to 16. So this last one is 13. Okay, so LINCOS is a great idea. I love it. But sadly, LINCOS has no model for the alien. No model for, I mean, what he sort of does is he says, well, this alien, if it's going to be able to read this message at all, has to have enough brights and enough intelligence to be able to be able to understand this stuff. But I would like to have a model for the alien. And so part of what I'm trying to do here is get a model for the alien. Polya, how to solve it. Polya has a wonderful book telling you how to go about doing discovery. It's great. But he has no model for the student. Well, you know, student, you're the student, I'm the student, but I would really like to be able to have some more well-defined model for the student. A physics problem, the relation between the period and the length of a pendulum. You remember, I remember in high school being absolutely amazed that the weight of the bob doesn't seem to matter here. But Galileo explains it beautifully. You know how he does it, how he explains it? He says, well, suppose you have two pendulums with a 1 kilogram weight. Say 1 meter, 1 kilogram, one pendulum, period about 1 second. Put another pendulum right next to it. Period is also about 1 second. Well, look, these two pendula are essentially the same as one pendulum with a 2 kilogram weight. So it must be independent of the mass. It's beautiful. It's not an induction, that's deduction of a sort. Okay, so lots of wonderful stuff in Galileo. Galileo, oh God, I love Galileo. I mean, it's, you know, you think about how the Earth is moving. If the Earth were split at some point in half, cut in half and connected by a thread, it would still follow the same orbit. It doesn't matter that the two halves are glued together or not. So Galileo knew that when he saw that the moons around Jupiter that the orbits of those moons did not depend on the size or the mass of those moons. It's absolutely, how wonderful that he would have discovered the moons of Jupiter, because he could have really enjoyed that fact. In fact, had he gone just a little bit further, he would have been able to figure out how light bends around the sun, because the same argument can be used to show that light bends around the sun exactly as Einstein said it would. He was really onto something wonderful. By the way, oh yeah, the whole point about this is, if you have, here's the length and here's the period, and you put them together, this sequence is in Sloane, but if you actually do an experiment and you come up with these numbers instead, say, for different units, so 7 gives you a period of 1, 28 gives you, the sequence you get is not in Sloane. I mean, this one is, that one is, 1, 2, 3, 4, of course that's in Sloane. This one is, because it's 7 times, I don't know, whatever, put them two together and it's not in Sloane. So this is an example of why I want an automated physicist. I want a physicist that knows about this class. I want this class of sequences. Really, there are two parts to what I want. I want a nice, well-defined class of sequences with the property that Sloane is really just a sample from that class. And the class should basically contain the sequences that really come up in science, but it should also have the property that any sequence in that class can be inferred efficiently. That's what I want. It can't be too large because I want efficient inference. Okay, that's Polya's how to solve it, a physics problem, fine structure constant. Oh, you know what the fine structure constant is? This is just wonderful, absolutely wonderful. There is a constant in physics called the fine structure constant. This alpha, known to the physicists generally as 1 over 137, approximately. For a while, it looked like it was 1 over 137.035999. You know what that is. See, it's worrisome, isn't it? I mean, but soon enough, they said, no, it's 0 after that. So we now know that 0 is for real. This fine structure constant, this 1 to 1, the ratio 1 to 137 is the speed of the electron around the proton in the hydrogen atom in the Bohr model. It's this ratio of the speed of the electron to the speed of light in the vacuum. Isn't that lovely? Fixed constant, independent of how you make measurements, independent of what your unit of time is, independent of what your unit of length is. The physicists on Mars would come up with exactly the same constant. Dimensionless. What?
Can you derive it from h bar and the speed of light and the mass?
Yes, it can, and it's dimensionless, but we don't know these things very well, so every so often we get another digit. And so here an application for what I want to do is, gee, you know, those digits are very expensive. It really costs a lot of money to get one more digit. But wouldn't it be wonderful to be able to come up with a nice, simple formula for explaining it? I mean, then you'd be doing physics. I want something that's more succinct than the actual digits. And the physicists would definitely like to know. Feynman said that he put this number up on his board, and every morning when he comes in, he looks at it and tries to figure out what the hell is this number? Where could it be coming from? They have not the vaguest idea. And and there are all sorts of calculators out there. Yep, 5 minutes, okay. Let's see, so where combinatorics and probability, that's another thing. Programs that learn from observation. Here's a nice computer science application. programs that learn from observation. You know, in Carnegie Mellon, everyone's interested in really provably correct programs. I'm running in the opposite direction. See, I got tenure, so I can afford to do this. I want programs that work like kids do. You know, you show a kid how to do multiplication. You don't give them the algorithm, for heaven's sakes. It would do them no good. You show them how to do multiplication of small numbers and maybe bigger numbers, and you hope that eventually he understands how to do multiplication. He's constructing the algorithm for himself. I would like programs that can do that, that like the kid can figure out, I'll just show it what to do, and it should figure it out. And I'm saying that if you can do this with the sequences, I'm hoping you'll be able to get programs that learn from observation. Okay, demons. A demon for periodicity, a demon for eventual periodicity. I got lots of demons. Demon for eventual periodic. Notice these demons, I got a whole huge list of them, because every night I take a new sequence from the online encyclopedia, I try to figure out what it is and ask myself what's the class of sequences that this is talking about. There's a demon for pseudo-periodicity, which is the one that splits a sequence into two parts. Lots of demons. Demon for polynomials. Demon for linear recurrences. Actually, polynomials can be written as linear recurrences. So you might, why bother with polynomials? But there's a reason, because a linear polynomial of degree d requires that you see at least d plus 1 constants. If you have a linear recurrence of degree d, you need to have 2d many values. So it's much more you need much more information. You see, it's expensive, and you don't want to have to do that. So we have both of them. Why take differences? You can use Gaussian elimination. If you know it's a polynomial or you think it's a polynomial, use Gaussian elimination. You could solve. No, take differences. Why differences? Because differences also work even when it's not a polynomial. Works, for example, with Fibonacci. Take differences on a Fibonacci, you get Fibonacci. Works on other sequences too. There are many sequences which, when you take differences, it simplifies it, and Gaussian elimination doesn't help. So lots of demons, they work together. I've explained this. This is an example of an application, and I'm just about done. This is an application where I would like to teach this program to recognize the fact that I start at some point here, and then I do this, and I show it what I'm doing. I've got these numbers here to show you how I'm going. You can see I'm creating a spiral, but I don't want to have to tell it I'm creating a spiral, because it doesn't understand English. But it can watch what I'm doing, and then write it out as, well, moving north, then east, then south twice, then west twice, then north 3 times, east 3 times, south 4 times. You see what's going on here. And the way the demons work is they put stuff together, and very soon it can create the spiral. So many examples like that. Modus operandi, lots of demons. Oh yeah, that was the hard one, A9 I have. This is another example where I'm going to teach the machine to go to the X and then make a right turn. Go to an X, make the right turn, go to the X. So it does something like this. I put in numbers, made it a little bit harder, because now when you're coming down at some point the 4 hits a 1, you leave the 1 in place just to make it interesting, and you can see, you can write down exactly what's going on. You feed it to these demons, and boom, they can see what's going on. Just very nice. What else? List of demons in no particular order. These are typical demons. More demons. More demons.
How many do you have?
I won't answer that question. I haven't even counted the number that are on here. There are Lots of daemons. The important thing about these is that all of these daemons have proven to be useful in several cases in Sloane. Anyway, that's it.
Thank you very much.
It reminds me of Doug Leonard's PhD thesis, AM, which he was
Yeah.
using heuristics to infer theorem.
What's going on? Yeah, yeah. It was very good. So when he was working on, oh, let's see, which one? That's the one that was inferring, that was, guessing theorem. Yeah. Yeah, I guess he was proving theorems because they worked for lots of cases, and
It worked for two cases.
that was good. Yeah, thank you.
So this all reminds me of the issue of Kolmogorov
Complexity, yes.
sequences, and it looks sort of sounds like a different take on how to approach this field. But then you ask yourself, why demons? You want to abstract what the automated physicist does. So here's the ugly but obvious abstraction. Take the size of the physicist's Turing machine, and that's your class. It's like very ugly. It's not intuitive to understand what the size of the Turing machine means exactly. But you could get like classes of what you can, what kind of sequences you can identify with smaller, larger Turing machines. So instead of that, you offer to consider this concept of daemons. And the question is, I mean, it's natural to think about them, but what's the methodological justification for thinking about daemons and combining them?
Well, Sloane has all integer sequences that have ever appeared in any book anywhere. So I view it as a database. It's a great and wonderful database, and I want to find the daemons that work for that. I'm not interested in general. I'm interested in the ones that have worked for science.
You want to cover the 200,000.
I want to certainly cover the 200,000.
Concise and
right. So the 200,000 are like samples from this larger space, and it is sort of like Kolmogorov complexity in the sense that once you find this algorithm for one of these sequences, you have really compressed that sequence, infinite sequences you've compressed down.
Just a small comment. I was not convinced at all by your visual proof that the period of appendix